Hello, hello, hello. Testing, testing, testing. Okay, I'm sorry about the background noise. Um, I've got to put the fan on, it's so hot, so um, it is what it is. So last time we went through this proof, um, and then we were going to need to do the exercises. So let's go and do the exercises. It says cross multiplying by the magnitude of w squared and taking square roots, the result follows. Exercise 1.3.3. When will this inequality be satisfied? Does this agree with your experience with arrows? So, let me just write that. 1.3.3. When will this inequality be satisfied? So it says, to prove the Schwarz inequality, consider axiom 1 applied to the following. We get that, where it's greater than or equal to 0, where we have used the antilinearity of the inner product with respect to the bra, where we have used the antilinearity of the inner product, the conjugate, I guess. Let me just double check that because I think that's what it means. When R. Shanker's book on exercise 1.3.3 states sorry, on point 1.3.18 states where we have used the antilinearity of the inner product with respect to bra using by antilinearity, is this referring to antilinear antilinearity? I think I have to say what is meant by antilinearity. To say that something is linear, I mean this equation, this state here, if we think of it as an arrow, we are taking away some angle between something and then dividing it by the square root of the inner product squared. So we're taking the length of something. We're taking, so this top part. Let's imagine this. This is WV, right? It's like so some theta difference. Wow, nice theta there. Oh wow, this is going well. Okay, the magnitude is the length of the line. Let's call this D, but this is going to be W2 actually. It should be just that. The vector W and V, well, W is a scalar to this, so whatever W does, At this point, we will make it either smaller or bigger, right? So this is a scalar, and then the v, of course, is going to be this. I mean, it could be a completely separate vector. It could be something like that, right? And we're going to take the result of this scaled vector made smaller by this. Well, yes, made smaller because it's always positive. Um, we're going to take that whole thing away from this. So is there any antilinearity in there? No, I guess there isn't because we've got two linear lines or two linear vectors. Um, I'm not seeing how that's not linear. So anti-linearity does not mean not linear. I'm sure I've probably asked this before. Let's see, anti. Let's see. Yeah, maybe not actually. Okay. Well, imagine this is a new thing. So I've hit the mark. Oh, by the way, I think I said last time, but I did report this problem where it's very laggy when it gets large, and they have responded and saying they've made a note. So let's hope it gets fixed because it's quite difficult really to use the browser whilst it's happening. So it says in the context of, sorry, what was it? I've got like acid reflux. I didn't normally get that. So it's something new to me, and I've been like loads of peppermint oils and like Gaviscon tablets, and I've gone to the liquid and just trying to like get it down. And I keep now yawning and burping. It's just so grotesque. So my apologies if I keep like muting myself to burp. Anyway, in the context of quantum mechanics and specifically in Dirac's bra-ket notation, antilinearity refers to how the inner product behaves when you take the complex conjugate of a scalar factor. It's funny. I said the conjugate, but I suppose it doesn't make too much sense to me. It's the reverse of what the vector is, isn't it? Because you're going to essentially negate the complex part of the number, or the scalar of the, well, yeah, the whole, yeah, basically the complex part. And so I'm not sure why that's anti-linear. So it says in the context of quantum mechanics and specifically in Dirac's bra-ket notation, antilinearity refers to how the inner product behaves when you take the complex conjugate of a scalar factor. Okay, fine. Um, Given any scalar c and any state psi, is that psi? Uh, Psi, Greek alphabet. Yeah, psi. The ket vector is multiplied by c as you'd expect. However, when you multiply the corresponding bra vector by a scalar, the antilinearity means that you have to take the complex conjugate of that scalar. So if you were to scale both the bra and the ket by the same scalar, c, you'd have uh, the conjugate multiplied by the normal equals the magnitude squared of the inner product. This property ensures that the probability interpretation of the quantum state remains consistent, the inner product gives the probability amplitude, and its magnitude squared gives the actual probability. When multiplying the state by a complex number, the magnitude, and hence the probability, should scale by the magnitude squared of that number. I'll read that again, it's not gone in. The inner product gives the probability amplitude, and its magnitude squared gives the actual probability. When multiplying the state by a complex number, the magnitude and hence the probability should scale by the magnitude squared of that number. The antilinearity ensures this consistency. Okay, interesting. So there's some deeper notion going on here, which I suppose we should really think about. Though, let's just continue through the words and see what we pick up from this. So it's saying that the conjugate is equal. Uh, so where we have used the antilinearity of the inner product, I guess it's going to be these kind of terms here. Well, actually, just this term, right? We find that the inner product of V is greater than the multiplication of the two inner products over the magnitude squared. So cross multiplying by W squared and taking square roots, the result follows. So when will this inequality be satisfied? Well, if we were to set the output of these two null vectors, so 0, and then you divide 0 by something, you get, I guess it's undefined, right? 0 divided by something is, 0, okay, cool. Yeah, it's interesting. I thought 0 divided by 1, 2. 0 divided by 0. I guess it's 0 divided by 0, isn't it? Yeah, okay. So actually, the magnitude of a null vector would be 0, so you're going to get undefined, which isn't possible, right? If we set these to 1, you're going to get 1 divided by 1, which is 1. Cross multiplying by W squared and taking square roots, the result follows. So here's the cross multiplying. Well, maybe not actually. What is this trying to say? When will this inequality be satisfied? When V is, if V was a null vector, I'm just trying to think about this before I plug in the numbers, because there's something profound about this. It's the fact that the inner products, the W must be something. The V must be something, sorry, because Otherwise, you're going to always end up with 0, right? Now, if W was something 2, um, if W was 0, but V was something. Yes, that's the one, isn't it? Let's say that. So, um, I think I just scribbled that out. It's a bit nonsense. So, let's take this following equation. V is greater than W W, and then over W squared, right? And this can only be true. Well, let's just imagine that I'm right for a second. I am seeing that if V was actually, V is 1 0, then the inner product of that would be 1 times 1 is 1, uh, plus 0 times 0 is 0, so it's going to be 1. And now let's take the idea that W, sorry, this is actually the vector V. Let's do that properly. So the ket V, let's take the ket W, and let's say that's 0 0 null vector. In fact, we can just say it's 0, but um, you know, like they say, but this is also equal to 0 0. And so now you've got a different thing, because you're going to have to do 0 times 0 plus 0 times 0 is 0. 0 times 1 plus 0 times 0 is null vector. Uh, so in this case, both of these would be 0 times 0 equals 0, and then you're going to divide by the magnitude of 0 squared, right? Um, which of course equals 0 as well. 0 divided by 0 is 0. And so indeed, 1 is greater than 0. Now, I don't know if that's what it's getting at, but that feels right to me. So does this agree with your experience with arrows? Well, um, sure. Like if you multiply by null vector, you're going to get 0. It says, when will this inequality be satisfied? Yeah, I don't think I'm on the right lines here. So the exercise 1.3.3 of our Shanker's Principles of Quantum Mechanics asks, when will this inequality be satisfied? Does this agree with your experience with arrows? The the idea I had was that if we take the following inequality stated in the book above, let's do this. It's going to be inner product of V is greater than W V V W divided by the magnitude of W. How do you do that again? Yeah, cool. I learned that from my friend. Oh, he used to play Jedi Academy, and this clan was called O2. And like the only reason I know how to write the 2 like that, the superscript 2, is because of that. Okay, well, we've got that, and let's see if that's right. VW. Okay, sure it was. So the idea I had was that if you take the following, if V was a a vector with anything. So let's say v equals 1, 0, and w was a null vector, w equals 0, 0, then the equation holds. Um, is this what the book is trying to get at? Who knows? Yeah, I guess I'll set you off. So the inequality of reference, commonly known as Schwarz inequality, is given as the magnitude of the two inner products. Oh, um, no, I'm not seeing that. Um, though, if let's just take a step back though, because the magnitude of the magnitude of w is the square root of the inner product. So if we take the square root of the inner product, and then square it again, you end up with the inner product. Let's write that down. So if you start with w, where w is equal to the square root of the inner products, right? Then then this squared is ww. Yeah, because if you go to if you do square root of 9 is 3. Wait, is that right? You know what, I'm just the worst. Just ignore me for a second. Square root, that one. That was wrong. Square root of 9 actually. Yeah, okay. So the square root of 9 is 3, and then you square it again, you're gonna get 9. So same premise is there. So let's imagine that part. Now how do we get the magnitude up here? Because they're saying that the inner products multiplied by each other is the same as saying the magnitude of them. But I think maybe also it's just saying the absolute value of it. Um, so I'm not too worried about that. I mean, it doesn't. Let's see. The inner products of two things um, is the same anyway, and then to take the magnitude of it, we have to square root it. It ends up being that anyways. It's the same. It's the same. Yeah, it's the same. No, 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 no. At that point, we have to square root it, and it's not squared. And furthermore, the bottom's right. Let's go on. So this inequality is true for any vectors v and w in a complex inner product space. It's a very general result. However, the specific question you're asking about refers to conditions under which the inequality becomes an equality. However, the specific question you're asking about refers to the conditions under which the inequality becomes an equality. Oh, oh, I see. So that's what that means. So when will this inequality be satisfied is actually saying when will this inequality no longer be unequal, but rather equal? The Schwarz inequality becomes an equality if and only if the vectors v and w are linearly dependent. One is a scalar multiple of the other. Uh, Linearly dependent, you can make something else out of both of them in the same vector space. That sounds right to me. Now let's relate this to arrows or classical vectors in the plane. When two arrows or vectors are pointing in the same or opposite direction, they are linearly dependent. The experience with arrows shows that the projection of one arrow onto another is maximal when they are aligned. This is in agreement with the quantum mechanical notion that the Schwarz inequality becomes an equality when the two states or vectors are linearly dependent. In your specific example, v is a non-null vector and w is a null vector. In this case, the inner product is 0 and the inequality is trivially satisfied. However, the more general and interesting case is when neither of the vectors is null and they are linearly dependent, making the inequality an equality. Right, so this I want to just double check the terminology here. So I see my confusion. You're saying that when will this inequality be satisfied actually means when will this equation be wrong, whereby the two sides of the actually equal each other. Um, I mean, that's what I just said. Let me just double check I just said that. Means when will this equation be wrong whereby the two sides of the equation actually equal each other? I mean, the equation's wrong if they equal each other because it says it's greater than. Oh, greater than or equal. I see. I see. Well done, GPT-4. We love you, really. I see. I forgot about the greater than or equals part. It's interesting because the book doesn't actually show the inequality as such. I mean, maybe it does. I don't remember it really. The Schwarz inequality, the magnitude of VW. Oh, yeah, it doesn't. It explains the Schwarz inequality as the W. So the magnitude of the inner product is less than or equal to the magnitude of V times the magnitude of W. It's interesting because the book doesn't actually show the inequality as such, um, as you have described it. It explains instead the Schwarz inequality as. Now, is that the same? Because let me see here. If the magnitude times each other is greater than or equal to the magnitude of the inner products together. I don't know about this. The form of the Schwarz inequality that you provided is indeed a commonly used and concise form. Now, this inequality will always be satisfied in the inner product space, but it becomes an equality when v and w are linearly dependent, or in simpler terms, when they are parallel in the vector space, including being anti-parallel, pointing the other way. For a geometric intuition, consider arrows or vectors in a 2D plane. If two arrows are orthogonal, their dot product is 0. As they become more aligned, their dot product grows, reaching its maximum when the arrows are perfectly aligned, either in the same or exactly opposite directions. This maximum value is just a product of their magnitudes. So, to answer the exercise 1.3.3, the inequality becomes an equality when the vector and v ket and w ket are perfectly aligned. This observation should indeed agree with your experience with arrows. If two arrows are perfectly aligned, the projection of one onto the other is maximal, corresponding to the product of their lengths. Okay, let's find the pen, and then we shall do that. Okay, there's the pen. So let me just move that across. Plot my little dots in. Okay. Fine. So first I'm going to draw it. It's saying that when V and W are parallel or anti-parallel, in this case anti-parallel, then they are equal. Now, it says about that word linearly dependent. Now, I never knew that linearly dependent is also meaning that. Like, it's quite simple now, isn't it? You don't really have to overthink it too much, which is nice. Let's do another one. It's also saying, yeah, when vector, when ket v and ket w are parallel, this 2 equality. Now, however, when they are not aligned, parallel or anti-parallel, let's say, for example, they are orthogonal to each other, then they are unequal. Yeah, cool. Let's prove it. So, if V is, let's see, it's going to be 1, 1, and W is my 1 minus 1. Now these should be therefore unequal. Let's prove it. So to make a note, Schwarz inequality is the magnitude of VW is less than or equal to the magnitude of V times the magnitude of W. Let's see. Did I get that right? Maybe. Ooh. VW. VW. Yeah, we got it right. Cool. So in this case, the inner product of V and W is equal to 1 times 1. Sorry. 1 times 1 plus 1 times minus 1. so minus 1, which equals 0. And so magnitude of 0 is 0. Magnitude of 0 is 0. And so 0 is less than or equal to, now let's do the magnitude of v is going to equal the square root of v, and so we need to do v equals 1 plus 1 equals 2, and so I mean we can already see it, but the square root is roughly 1, was it 1 point something, let's see, square root of 1.4, and so I mean obviously, well, maybe not so obvious because you've got the negative in there. Let's just do this. Um, so let's do now uh, the magnitude of w is equal to the square root of w, and so um, that's 1 plus 1 negative 1 is equal to 0. Square root of 0 equals 0, and then we're multiplying them together. So, oh, now hang on a second. Now hang on a second. It's saying that it's less than or equal to, but this is saying that this should now be unequal. It comes in equality when v and w are perfectly aligned. When v and w are linearly dependent, or in simpler terms when they are parallel in the vector space, including being anti-parallel. Well, they ain't parallel, that's for sure. I must have done something wrong. I trust GPT-4 here. So v, the inner product of v and w is going to be, it's 1 times 1, 1 times negative 1, 1 minus 1 equals 0. Yep. And any operation on 0 is going to equal 0. Um, yeah, because even if you took the inner product with the VW itself, then it would end up with 0, the square root, doesn't matter. So the second one, so this probably looks about right, I'd say. This looks about right. Book. So the second one is, if we're doing the magnitude of v, then we've got to do 1 times 1 plus 1 times 1 equals 2. The square root of 2 is 1.4. And w is 1 minus 1. And that would be 1 times 1. Ah! We got it! Alright, here it is. So it's going to be 1 times 1 plus negative 1 times negative 1. So it's actually going to be plus, isn't it? It's 1 plus 1, which is equal to 2. Let's just double check that, because I'm an idiot. 1 times negative 1. Yeah, that was not right. Let's try that again. Negative 1 times negative 1 equals 1. Yeah. So then it's 2. And so the square root of 2 is 1.4. Now 1.4 times 1.4 is bigger, right? Whoops. 1.4 times 1.4. So VW equals 1.4 times 1.4, which equals 1.96. And so left side 0 is less than or equal to 1.96. Bada bing. Good. And I think that's already kind of obvious that the straight line will be the same. But do I want to do it? I mean, yeah, why not? Why not? So let me just scroll up a little bit actually, so I can keep all my bits and bobs here. Something like that. Oh well, maybe like that. Yeah. And so that's that. That one's that. Now let's go for equality. So if v was actually equal to 1 1 and w was equal to 1 1, they would therefore be, they're both on the same thing. They're both parallel, so that makes sense. Then the inner product of that is going to be 2. Sorry, the magnitude. So let's just do it. So VW is equal to 1 times 1 plus 1 times 1, which equals to 2, and then the magnitude of 2 is 2, and then that's going to be equal to the other side, because the v would be this, and w would be this, which means this is the same thing, right? It's 1.4, roughly 1.4, and then roughly 1.4. You're gonna get roughly no, yeah. Hang on a second. That's interesting, isn't it? Because we end up with 2 for the inner product. Square root it, you get 1.4. And so that's roughly VW equals 1.96, which it doesn't equal 2. Um, which it would have to be equal. No, no. This is me rounding. That's why. Um, let's do this properly. If I were to do um, square root of 2, oh, for goodness sake, square root of 2 times square root of 2, then we get 2. Okay, cool. Good. Roughly, so it says roughly 2, tick. So it's actually equal to 2, equals 2, tick. Right? So that's great. So they are equal. So, okay, we've seen it. So indeed, when you do it, that meets the expectations of the arrows. And when will this inequality be satisfied? As GPT-4 says, it'll be satisfied when they are uh, perpendicular. Good. That's fine. I don't have to prove anything to myself there. So now 1.3.4, prove the triangle inequality starting with v plus w squared. You must use re v w. You must use re in product of vw is less than or equal to the magnitude of them and the Schwarz inequality. Show that the final inequality becomes an equality only if ket is equal to a scaled version of w, where a is a real positive scalar. Cool. Okay, I'm looking forward to that. Um, I want to do it. I think I'm just gonna have to sit down though, because my legs are hurting. Right. So let's do it. Just gonna move this over on my screen. Put my little dots. Prove the triangle inequality. So let's remind ourselves of the triangle inequality. I think it's trying to do it there, but um, triangle inequality equals the the um the magnitude of the addition of the vectors is less than or equal to the magnitudes plus each other. And then it says prove the triangle inequality starting with v plus w squared. You must use the Schwarz inequality. Show that the final inequality becomes an equality only if v is equal to aw. I have never written a mathematical proof, so this will be fun. Just having to think about this. We need to say a lot of things that I might not understand. I might not have the tool set in my head to do this. So we might need to use GPT-4 here to guide me. Having said that, show that the final inequality becomes an equality only if the vector is the same as is equal to the scale of w. So what it's saying is that any scalar of that parallel or anti-parallel vector, so as long as w is anti-parallel or parallel, then scaling it by a is going to make the same vector. Yeah, not magnitude, but vector. So we know that to be true because we just did it. So how do we prove that? Because it's saying about v plus w squared. So it says start with v plus w squared Well, if we're adding two vectors to each other, let's say they're like this, then we end up with this new vector, right? Then if we take the magnitude of that, it's going to be, some proportion of this and that longer, and then you're going to square it. So it's going to get much bigger. I mean, how would I prove this without knowing maths? I would simply say, because you can't plug in real numbers to this, you need to say, given this logic, this must be true. Show that the final inequality becomes inequality only if the two that equation is so. So we need to say, well, like what if they're not equal? Then this would happen, and we can kind of say that because the Schwarz inequality uh, has an equal sign in it, but it also has this less than sign, so it's up until the inner products are so if the inner products are 0, then they are perpendicular. Now, at 0, it's trivial to say that they're going to be equal to each other. So if the inner product is 0, then the magnitude of something is 0. Um, and so that's one way of saying that if they're if they're not parallel, if I just go back a second, because we said that there is equality when they're parallel, and when they're perpendicular there's an inequality. And this makes sense. It's saying, because we just did the inequality would be equal to this 0 is less than or equal to 2. So because let's go back to our triangle inequality. Because the vectors must be uh, let's say 1 1 1 minus 1, then adding them together is going to be 2 1 plus minus 1 is 0. And then the magnitude of that is 0. And then the magnitudes plus each other would be, I might need to reflect on this a bit. because I'm not sure what I'm saying here. I'm saying that the left side would be 0, and then if you did the magnitudes, you would get um, 2 and then 2. You'd end up with 2 on the right hand side, so it'd be 0 is 2, so 0 is less than or equal to 2, which is true. And the reason we know that is probably not, it's probably not what they want to show here, because their proof is, they're saying if the inner product is like, yeah, I'll need GPT-4's help here. Um, I'm not feeling so great, so I'm going to stop streaming here. But it was good nonetheless to get through exercise 1.33, and we'll come back to the 134 at a later date. So thanks for watching, and speak to you.